Okay, so we'll go back to another video. So today we have an improper integral and we have a combination inside of our integrand are the complementary error functions. So we have the complementary error function square of x and then add this with just the complementary error function of x. So a lot of the values and the rewriting that what we'll be doing relies heavily on the definition of the complementary error function. You can actually write this in terms of the error function itself too. And proceeding forward with all this, it's actually going to be a lot of integration by parts utilizing this. The strategy here, however, is that we're actually going to be taking into the linearity of things and instead calculate two of the integrals separately. So actually, first we're actually going to calculate the integral of this, and then later we'll be actually calculating the integral of this, because the follow-up to the values that we will be using is utilizing the calculations from here when we calculate that integral. So a lot of the values we'll be using will be utilized as well, and I'll actually, before we actually get to the meat of that, I'll actually write everything in the values for, the important information we'll be using to, further help support what we're doing from here. So with that out of the way, let's actually just jump right in. Okay, so everything I've written down is going to be some important information. So we have that the complementary error function of x is written as this integral over here. So it's basically similar to writing the error function, but the bounds are different. But in other words, you can actually write this in terms of the error function 1 minus the error function of x. And if you were to take the derivative of this is actually going to come in handy. As I mentioned, there's going to be integration by parts involved, so we want to put this down anyway. Then you just simply apply the fundamental theorem of calculus involved, and then you get this value. And some important values you plug in for 0 and infinity, right here, 0 and infinity, you get that if you plug in 0 as 1, infinity is equal to 0, and to supplement this as well, we have the error function of infinity and the error function of 0 is equal to 1 and 0 respectively, and I also wrote down the definition of the error function in terms of this integral as mentioned as well. So that'll be the important things we'll be using, so why don't we actually start by integrating this piece first. So we're actually going to be calculating the integral from 0 to infinity of the complementary error function of x, then dx. As you can see that if this doesn't look as difficult, this might look a little uneasy from this perspective. But what we can do is we can actually apply, as I mentioned, integration by parts. So why don't we choose a u and a dv to choose from over here. So I think it's clear that in order to choose our u and dv, we're going to let u be the complementary error function. So afterwards, we got to take its derivative. So what we have is that, of course, I wrote this down for a reason. So that means du is going to equal to -2 divided by the square root of pi multiplied by e to the power negative x squared, and followed by dx. Then next we choose our dv, we can let that be dx, and then v is just equal to x. All right, so we just put this back together. So now uv is going to be v times this. So that means x multiplied by the complementary error function of x. Evaluate this from 0 to infinity, and then we can actually just subtract, but also we can actually factor out this minus over here, so that means this is going to be a plus. And then we have a 2 divided by square root of pi, so that can also be factored out outside as well. So 2 divided by square root of pi. Then we have our integral from 0 to infinity, so x, and then multiplied by e to the power negative x squared, and then dx. And so from here, if you plug in your bounds, if I plug in infinity, so that's going to be over here, that's going to be equal to 0, but I also have an infinity times 0. Same thing, so 0, and then that's actually going to be also equal to 1. When you plug in 0 over here. But the thing is that we have an indeterminate form once we plug the infinity over here. Simple enough that you just apply L'Hopital's rule after you convert this into a form of a rational function. When you take that limit, you get an indeterminate form, of course, then you have to take the derivative of both the numerator and denominator after converting this, and then eventually once afterwards you apply to all that, you're going to get that this whole thing is actually just going to be equal to 0. So what we're left with is just this value to calculate. And this one's not so bad after all, because the following over here, x times e to the negative x squared, is actually a simple calculus exercise by applying the u substitution. For over here, we're going to let u equals x squared, and then of course we let du equals 2x dx. So then over here, if you actually put everything back together, so now I have that this is actually just going to equal to 1, then divided by the square root of pi after you divide that 2 from outside. Then the x dx vanish, and so we're just left with 0 to infinity. Change your bounds, but you're still going to get the same thing either way, so that's okay, of e, and then to the power negative u, and then du. Simple that this is going to be negative e to the power negative u. If you plug infinity and then plug in 0 afterward, take the subtraction, we get that all this is actually just going to equal to 1 divided by the square root of pi. Okay, So that actually just gets rid of that. So let me actually first box that first part of our answer that we actually, calculated, because this is actually going to be important for later. So with that in mind, now let's actually move on to calculating the complementary error function square. And it actually just follows by the same thing that we've just been applying the technique here. So now what we're dealing with here is actually going to be from 0 to infinity, complementary error function square of x dx. Of course, we do the same thing. We're going to integration by parts. We're going to let u equals the complementary error function square of x. And so what that means is that du, so if you differentiate this, you would apply the chain rule. So that means it's 2 times this, and then you have to take the derivative of the inside. So basically take the derivative of the complementary error function, simplify everything out together. We're going to have that our du in this situation over here is going to be equal to -4 divided by the square root of pi multiplied by e to the negative x squared multiplied by the complementary error function of x and then dx. And then of course, if we choose our dv, we're going to let that be dx, and then v is simply just going to be x. So put everything back together. So now I have x multiplied by the complementary error function square of x. And then if you evaluate this from 0 to infinity, you actually do the same. It's actually a similar reasoning, just like from over here. You have to convert this into a rational function, then take its limit, you get an indeterminate form, take the derivative of the numerator and denominator from that, and then we actually get that this whole thing just is going to approach 0 from applying L'Hopital's rule. I forgot to say L'Hopital's rule for the wrong one, but that's what you use for this situation as well. So this out of the way, so now let's actually simplify everything for the integral of v du. So afterwards, if you put all that together, so I have a plus, since it's a minus, and then I factor out that negative, so that's a plus, and then factor out the constant, so I have 4 divided by the square root of pi multiplied by the integral from 0 to infinity of x times e to the negative x squared, and then times the complementary error function of x, and then dx. Okay, so this is what we're left with. So you might be thinking, how can we actually tackle such improper integral? Well, there's actually a reason why the complementary error function of x is actually, in other words, the same thing written as 1 minus the error function of x. What we're going to do is instead we're going to replace with this and then substitute it back here. And it makes things easier such that I can actually, so not only substitute, but distribute the x to the e to the negative x squared to all of that. And what that does is that we can also break this up into applying the linearity as well. So we're actually dealing with 2 integrals to calculate. So why don't we actually do that? And also I could just factor out the 4 divided by square root of pi. So now everything over here, so I have 4 divided by square root of pi. So afterwards, applying the linearity, so first we're going to have 0 to infinity of x times e to the negative x squared. That's just distributing this from the 1, and then dx. And then afterwards, we can subtract this. So now this is going to be the integral from 0 to infinity of x e to the negative x squared, and then now multiply with the error function of x, and then followed by dx. So let me close that off. Okay, so now that we have this, so why don't we actually first take a look at this integral, because actually just from earlier, we already calculated this integral to begin with. We know that this is actually just going to equal to 1/2. So with that, now we can actually, that saves us the trouble, and we can just focus on this integral over here. So now over here, what we're looking at is now if we actually do a u sub, so why don't we actually let u equals x squared. So that would have to mean that du is simply just going to equal to just 2x dx. Okay, not a big deal. Then I can actually just factor out that divide the 2 to both sides and factor that out. So I get a 1/2. So it's going to be 1/2, and then multiply by the integral from 0 to infinity. So bounds doesn't change, thankfully. So then I would get e and then to the power negative u. Then I would have to actually solve for x on its own because of that. So that means after doing so, we have the error function of the square root of u and then du. Okay, so afterwards we have this. So where do we go forward? We're gonna actually have to do yet again some more integration by parts. As you can see, I think the easier way to take the derivative and to take the integral is that we let this be u, and then we let e to the negative u be our dv. So if I take the derivative of e to the square root of u, so now let me actually use a different variable for this. So we're gonna let dw, or rather, first we're gonna let w equals the error function of the square root of u. So if you actually apply the differentiation, so utilizing that definition over here from the error function itself and then just apply the fundamental theorem of calculus afterwards, we're going to get that dw is going to equal to 1 divided by the square root of pi times u inside that square root multiplied with e to the negative u and then du. Then next is that we have dv. So dv equals e to the negative u, and then du, then b is just simply just gonna be negative e to the n to the negative u. Okay, so now let me actually get rid of the top half, and then we can actually continue moving forward. All right, so if we actually put everything back together, so now we have that the equal is just gonna fall from over here. So putting things back together, I have a negative 1/2 multiplied by e to the negative u, and then multiplied by the error function of the square root of u. And if you put in the bounds, so evaluate the bounds, luckily we don't have to apply L'Hopital's rule because everything is in terms of a value. So, but actually it actually just vanishes as just 0. So that's out of the way. And then now continuing forward, I have now is a subtract, but then factor out the, yet again, the negative. So I have a plus and then 1 divided by, factor out the terms, or rather, we factor out the square root of pi over here. And it's also distributing the 1/2 just from earlier over here. So that's another step ahead. Then we have 1 divided by 2 times the square root of pi. And then now multiplied by the integral from 0 to infinity of 1 divided by the square root of u, and then times e to the negative 2u, then du. Okay, so we're actually just about getting there. Again, I said that this is going to vanish to 0 after you plug in the bounds. No L'Hopital's rule, no indeterminate form needed for that. So continuing forward, that we're just looking at this. I'm actually going to write the square root of u in terms of like a rational, or well, in terms of an exponent. So putting all this, that means I have 1 divided by 2 square roots of pi, then the integral from 0 to infinity of what u to the power negative 1/2, and then divide it and multiply with e to the negative 2u du. Looks something similar, doesn't it? Well, let's actually we're actually going to do another u sub. We'll actually put this in terms of v. We're going to let v be 2u, and then dv is simply just going to be 2 times du. So divide the 2 to both sides, so at least that gets rid of that. And then we have to substitute this in terms of u. So that means if I solve for u by itself, I have u is equal to v divided by 2. So in other words, that means that's basically saying v divided by 2 to the power negative 1/2, which is just v to the negative 1/2 divided by 2 to the negative 1/2, which is basically just the square root of 2. I factor out outside, and I also factor out the 2, so that means now afterwards we're going to have now just the square root of 2 and then divided by 4 times the square root of pi, and then now we have 0 to infinity, so the bounds don't change thankfully. So a v and then negative 1/2 multiplied by e to the negative v and then dv. And then this actually follows a nice definition. This is actually the integral representation of the gamma function. And if you plug in the values correctly, we have the square root of 2 divided by 4 times the square root of pi multiplied by gamma of 1/2. And then gamma of 1/2 is a well-known value such that that's actually just going to equal to just square root of pi. And then if you simplify it down, I have square root of 2 divided by 4. In other words, that can be written as the same thing as 1 divided by 2 times the square root of 2. Okay, so that basically just calculates these complementary error function square of x. So we actually have our 2 values. We have this value and then we have this value. Well, actually, I take that back. We're not done yet because that actually, we just have to substitute this back into over here and then we actually distribute it. So first over here, that's actually now we put everything 1 divided by 2 times the square root of pi, or square root of 2, my mistake. Then afterwards I have 4 divided by square root of pi and multiplied with 1/2 minus 1 divided by 2 square root of 2. And then if you simplify all this out, we have that this is just 2 minus the square root of 2 and then divided by the square root of pi. We basically have everything. We have this value and then this value, so we just add things together. I'm going to call this whole thing capital I over here. So now capital I, aka, is equal to 1 divided by the square root of pi. Add this with 2 minus the square root of 2 divided by the square root of pi. In other words, that simplifies down to just 3 minus the square root of 2 divided by the square root of pi. And that is indeed our final answer for the sum of our complementary error function / integrand that we're actually working with. So that's an interesting value that we actually do, utilizing a lot of integration by parts and then utilizing values, the special values over here. And it's nice that we have a gamma function involved. So yeah, that's pretty cool if you ask me.